Hello. Well, this is the regulation of glucose, part 3. And I noticed that I made a mistake when I made part 2 and when I did part 3 earlier. And I'm going to correct that mistake now. So, fructose 6-phosphate is bound by phosphofructokinase, PFK, the enzyme that catalyzes that reaction to make fructose 1,6-bisphosphate. This part right here is in the wrong place. I need to move it up to here. So fructose 6-phosphate has two fates. It can bind to phosphofructokinase and make fructose 1,6-bisphosphate, or it can bind to a different enzyme and make fructose 2,6-bisphosphate. So this section is in the wrong place. It needs to be moved up. So let's erase it. Okay, erased. That feels better. Okay, I'm going to continue and fill in some more important parts of glycolysis. So after we have two phosphoryl groups on, it immediately gets cleaved into two parts, dihydroxyacetone phosphate and glyceraldehyde 3-phosphate, GAP. And these are in equilibrium. And there's another equilibrium here, the triose isomerase. And then there's several steps, and we get to pyruvate, the end of glycolysis. Anaerobic glycolysis continues with lactate on this side. Now it turns out that pyruvate can be changed into alanine in one step. Alanine, an amino acid, alanine. And pyruvate can continue down acetyl-CoA. Acetyl-CoA combines with oxaloacetate to make citrate. Now the reason I bring in alanine and citrate is because some of the amino acids, some of the regulated enzymes of glycolysis are regulated by alanine and citrate. Both of them inhibit glycolysis. And the reason for that is because, remember, glycolysis is not only regulated by the energy charge, but also by building blocks. Well, pyruvate can be used to make alanine, which is a building block for proteins. And citrate is the first molecule of the citric acid cycle. And a lot of molecules in the citric acid cycle, the intermediates, are pulled off to make and build different biomolecules. So citrate is a signal for plenty of building blocks. And if they're already plenty, then we don't need to use glycolysis to make more of them, so we should slow down glycolysis. Same with alanine. It's a signal for plenty. We've got plenty of alanine. That must mean we've got plenty of protein that's already been made, or we've got plenty for building blocks for making it, so slow down glycolysis. We don't need any more. So let's make a table. I'm going to make a table that shows the regulation of each of the enzymes, the regulated enzymes. So glycolysis regulation, and we'll have on the left side the enzyme names, and on the right side how they're regulated. So we have hexokinase that's found in muscle, and in liver there's a little bit of hexokinase, but also in liver there's a lot of glucokinase. And glucokinase is an isoenzyme of hexokinase. They have different amino acid sequences, and they are regulated differently, but they catalyze the same reaction. They both bind to glucose, they both make glucose 6-phosphate. So hexokinase is mostly in muscle, and it is inhibited by its product, so feedback inhibition. Glucokinase is not regulated by glucose 6-phosphate. It is regulated by phosphorylation. If you put a phosphoryl group, a kinase puts a phosphoryl group on it, it'll be slowed down. So that's in the liver only. And hexokinase is found both in the liver and in muscle, but not very much in the liver. Okay, next we have phosphofructokinase, PFK, and we learned that it's inhibited by high energy charge, so inhibited by ATP. It's activated by AMP, and in muscle, it's inhibited by a low pH. And that is in muscle only. And that's because when muscle is contracting anaerobically and making lactic acid, the acid in the muscle cell is building up and lowering the pH. If you lower the pH enough, the proteins in the cell will start to denature and the cell will die. So you can't get the pH too low, so you can't do anaerobic glycolysis for very long. When the pH gets too low, that's when your muscles start to burn and you're like, I can't go any longer. Glycolysis is stopped. PFK is inhibited by the low pH. Glycolysis stops, ATP is no longer being made, and your muscles can't contract anymore. You've got to stop your exercise. Okay, we talked about citrate being a sign of abundant building blocks for synthesis. Remember, the liver is in charge of synthesis, so only in the liver is citrate going to be inhibitory. Okay, and we learned earlier that, or did we learn this earlier? Well, it's true that, we're going to talk about this, I guess, now, fructose 2,6-bisphosphate also activates PFK, but this is in the liver only. So we'll talk about that in a few minutes. Let's continue this table. Continue finishing it. We've got pyruvate kinase is the third enzyme that's regulatory. We learned that it's inhibited by high energy. It's also inhibited by alanine, which is a signal that there's plenty of building blocks. It is activated, we learned this earlier, by fructose 1,6-bisphosphate, feed-forward stimulation. And in the liver only, it's inhibited by phosphorylation. Okay, that's in the liver only. All right, well, let's go back to looking at PFK. Remember that, I'm going to maybe use red here. Fructose 6-phosphate binds in the active site, and also PFK needs ATP. ATP is a substrate. Fructose 6-phosphate is a substrate for phosphofructokinase. ATP also inhibits phosphofructokinase. So it's both an inhibitor binding to the regulatory site and a substrate binding to the catalytic site. So let's go back to the PowerPoint. This is the reaction velocity graph for phosphofructokinase, the enzyme, and it's the reaction of the enzyme on the y-axis versus the substrate concentration. So you know that as you increase the substrate concentration, the velocity in green goes up hyperbolically. You know that if a allosteric inhibitor binds to the regulatory site of the same enzyme, the inhibitor will cause a sigmoidal shape instead of the hyperbolic shape, the red shape. So ATP here is binding to the regulatory site. At low ATP, there's no inhibition, so we have the green line, which is higher velocity at any fructose 6-phosphate concentration. As ATP concentration increases, it will bind to the regulatory site and shift the velocity to be lower at any fructose 6-phosphate concentration, so we have the sigmoidal line. You also know that AMP can kick ATP out of the regulatory sites, so it'll diminish the inhibitory effect of ATP. Why is it that AMP is chosen instead of ADP? Because in your cells you have a special kinase that can react two ADPs together to make an ATP and an AMP. So really, and this saves some of the ADP to become ATP again, so the muscle can continue to contract. But when it does that, it makes AMP. So AMP is really the indicator of low energy in the cell. Okay. Whoops. Oh no. I hate it when I do that. Now I have to scroll all the way through to try to find the right slide again. We're getting there. Okay, so here's the phosphofructokinase again with its allosteric sites where ATP binds, but the catalytic sites also where ATP binds. So regulation of PFK in the liver cells. Recall, liver cells need small molecules for biosynthesis. Liver does not usually do anaerobic glycolysis, so there's no need to monitor the pH or have the pH change the activity of PFK. Liver regulates blood glucose levels. So, and we've already seen this, PFK is inhibited by ATP in the liver cells, inhibited by citrate in the liver cells. It's activated by AMP and activated by fructose 2,6-bisphosphate. And this is in the liver only, and it's a feed-forward stimulation. So fructose 6-phosphate can be made into fructose 2,6-bisphosphate, which shows that there's an ample amount of fructose 6-phosphate and glucose. So phosphofructokinase needs to hurry up. So this fructose 2,6-bisphosphate activates the PFK enzyme. We're going to talk about this a lot more when we study gluconeogenesis, and it's going to get more complicated. So reminding us of the regulation at the entrance, hexokinase. And I think I'm out of time. I forgot to set my timer, so I'm going to end this here.